A bit of business to finish up from last time, so I spent maybe 10 minutes on that before moving on to the third lecture. The third lecture will be a little bit more about physics, not so much technical stuff. But okay, last time I ended, I think, about here. So we had been talking about the fact that you can carry out projector quantum Monte Carlo with valence bonds. I told you about the properties of valence bonds and the valence bond basis. And I don't want to get into too much details here, but the point was that we can do projector simulations. We want to project out the ground state, and we want to compute some operator expectation value. And I denote my projector like this. So this is a long string of operators. So we have n operators, and of course I have to check the convergence to the ground state as a function of this n. So n could potentially be huge, like millions, right? Okay, and then if n is big enough, we project out the ground state from the left and from the right and the left, the Brown-Ket state. And then pictorially what we have is something like this, where these are the singlet projector operators that make up the Heisenberg Hamiltonian that we're considering here. So you see here that these operators, if they act between bonds, they reconfigure the bonds. So we get here something in the middle, which is one of these transition graph loops where we overlap the bond configurations, and the expectation values we compute can be defined on those transition graphs. So what we are sampling here in our simulation would be, these operators, and now these are the full singlet projector. So in the SSE method, we split up the singlet projector into its diagonal and off-diagonal terms. Here it's the full singlet projector that had the properties we discussed, and we just sampled the locations of them. So the number is fixed. We just move around their locations. Okay, it turns out that this is doable. It works quite well, but it's not the most efficient way to do it. So a really nice thing is that one can actually make it look very similar to the SSE method by basically putting the spins back in. So a valence bond means up, down, minus, down, up. It turns out that the sign always cancel out if we put the spins back in, so you can really sample the singlet. So with probability 1/2, it's up, down, and probability 1/2, it's down, up. And again, the signs cancel out. Let me not get into the details. But in the end, we get, unfortunately, these two pictures are not for exactly the same system size, but instead of this kind of picture, if we put the spins back in, we do have valence bonds still at these trial states, but now you see I have picked up, down, or down, up here. So that's now also sampled, and then everything becomes very similar to what we had in the SSE method at finite temperature. The only difference really is in the SSE method we had periodic boundaries in this time direction, whereas now we have boundaries that are capped by these valence bonds. And you can see that the valence bonds now act as part of the parts of the loops as well, because we can form a loop here. When we come to an edge, we actually use the valence bond to determine where we go next. So the valence bonds valence bond basis is very natural to use for the trial states in projector simulation. So if we do it like this, the only thing that's left really of the valence bonds is the trial state. Okay, but then actually we can still take advantage of the fact that when it comes to actually measuring something, we can go back to the full operators here. So here we have diagonal and off-diagonal operators, but when I want to measure something, I can actually put in the full operators and again look at transition graphs. Okay, so you can read details about that in that paper. So then, the key again to why this is very efficient is that we can use these loop updates that we discussed last time, so one can make very big changes in one go in the system. Okay, so if I just again compare side by side what we have done finite temperature SSE where we have this kind of picture, and we have done the ground state projection, which initially looks like a quite different starting point, but if we use this relationship between the spin and bond basis, again, the pictures look quite similar. And really, if you have implemented one of them in a computer program, it's very easy to change and go to the other one. Now, what's the advantage of using the projector? So the projector scheme we want to use, of course, if we are interested in only finite temperature, only ground state properties, right? We can also get the ground state properties in the finite temperature formalism by going to large enough beta, as I showed you last time. But there's one advantage here. When we do this finite T method, we use the full Hilbert space, whereas this automatically restricts us to singlet states, right? So if we think in terms of converging to the ground state, we have to make sure, for example, that the temperature is below the smallest gap in the system. And the smallest gap is normally between the singlet ground state and the triplet excited state. In this way, we have completely gotten rid of those higher spin states. So this will converge faster. So, okay, so now this converges as a function of m, and this as a function of beta. So you have to translate between these two, and let me not say exactly how that works. Well, basically, you should think of this beta here as m divided by the system size n, roughly. Anyway, so this converges faster because we can build in some quantum numbers. Not only spin, but also we can use trial states that are translationally invariant. Normally, they would have momentum 0. And normally that would be the momentum sector of the ground state that we are looking at. So we immediately throw out a lot of states that would state in this case. Okay, so let me show some examples of what we can do with this projector method, and this is also something that is good to remember when we talk about quantum phase transitions later today. So the two-dimensional Heisenberg antiferromagnet, if we want to study its ground state, we may be interested in its order parameter, which is the sublattice magnetization, which I define as a vector operator here. So if we are looking at finite systems, we should look at the squared order parameter, because if we don't break any symmetries in the simulation, as we don't do, and we have a finite system, the expectation value of m itself would vanish, but m squared does not vanish. So what we want to do is to look at the expectation value of m squared as a function of the system size and extrapolate that to infinite size. Right, so we do QMC, so we do finite size, but there are no approximations in the methods I've discussed, and we just have the finite size that we need to extrapolate away. Okay, so it has been known for a very long time already that this system has long-range order in the ground state, and roughly what it is. So the order is not the perfect Nell order as illustrated here, but these spins fluctuate because of quantum fluctuations even at 0 temperature. So the value of ms, if you just take the square root of the finally extrapolated value, you get something like 60% of the maximum value. So these are some calculations that were done in the paper I already cited before, where just illustrating how we actually analyze the results in practice. So we compute the squared order parameter, or we can also look at long-distance spin-spin correlation functions. If we normalize properly, those will extrapolate, both will extrapolate to the infinite size order parameter squared. So you see here that they do. So here I plot as a function of one of the system length, and these are fits to, if I remember correctly, cubic polynomials. So it's known from spin wave theory and other arguments that the leading size correction should be proportional to 1 over L, and you can see that it is. But to really describe the data, you need to add additional corrections as well. And here the error bars are really small. So again, here's an illustration where I take one of these curves, I think it's this one, and I look at the difference between the data points and the fitted curve, and you can see that it looks, quite good, consistent with statistical fluctuations, and the deviations are really very small, something like 10 to the minus 6 typically. So the extrapolation also gives us a very accurate value if you ever need that. Actually, it's useful if you want to benchmark other methods and so on, where you may have some approximations. This is also very close to the spin wave, the value you get from even linear spin wave theory, the harmonic approximation, as we heard about in the last lecture. Okay, so now that's the Heisenberg model. Let me say a few things about this JQ model, which has, at least for some range of parameters, has a different kind of ground state. It has a valence bond solid or dimerized ground state. So when we look at the Heisenberg model, I have often mentioned that the exchange interaction really is similar to a singlet projector operator. So this is a singlet projector on the sides I and J, and minus that is the antiferromagnetic Heisenberg interaction. So now what we can do is we can take products of such singlet projectors, and we want to sum them up on the lattice in such a way that we don't break any symmetries by hand. So we want to preserve all the symmetries, for example, of the square lattice. So we could have, products of 2 singlet projectors, 3, or however many we like. So in the simplest case, we would just use this as our J term, the Heisenberg term, and this would be our Q term. And again, since we don't want to break symmetries, we also have the one where we have these projectors on the horizontal bonds. So now we have can look at the ground state of this system as a function of Q over J or J over Q. And one finds that there is a phase transition between this Nell state and the dimerized state. So this model is really constructed in order to be able to study this kind of phase transition without sign problems, right? So if we want to study some two-dimensional model with J1 and J2 interactions, as I talked about during my first lecture, we have sign problems in the QMC, so we cannot go to big system sizes. This doesn't have a sign problem. And we can study, the properties of the valence bond solid and this transition. And I will talk about this transition a bit more today, and also in the colloquium I will give on Friday. I will give the latest on this phase transition. I will say a few things today still. So if we think about how to do the simulation for these JQ models, it's actually very easy to generalize it from the SSE or projector methods I already discussed for the Heisenberg model, because these Q terms are built up out of singlet projectors as well. So for the Heisenberg model, we have this type of vertices as we discussed last time. And now we have for the Q2 term, which has 4 spin interactions, two singlet projectors, we have this diagonal vertex here, and we have a mixed diagonal, off-diagonal, 2 of them here, and we have a completely off-diagonal vertex. And here I show when you build loops, how the loops will go when they encounter these vertices. So it's very similar, actually, technically, to implement it. And one can do this in 1, 2, or 3 dimensions. It turns out that in 1 dimension, this model has a dimerization transition exactly of the same universality as the one that we talked about on Monday, the J1, J2 Heisenberg chain, where I showed you those level crossings and so on. So one can study this model and conclude that it has the same physics. And in 2 dimensions, as I mentioned, you have this Nell to VBS transition, so that may be also similar to what the J1, J2 model does in 2 dimensions, although that still is not completely clear. But one point here is that you can arrange these singlet projectors on the lattice in different ways. So this is what I already mentioned, that in the simplest case, the Q term has this kind of arrangements, and you can also do what we call the Q3 interactions, where you have these arrangements. And these seem to lead to continuous transitions between the null state and the dimerized state. But you can also do other ways. So this is based on work actually done together with Arnab Sen a few years ago, where he studied the Q term in this kind of staircase fashion. And in this case, the transition becomes very strongly first order. And we can actually understand why, because this, I should not go into details now because we need some more information to get the point, but John talked about the dimer models yesterday, and the dimer models have this emergent U1 symmetry, which has to do with the fact that these plaquettes can resonate. So you can resonate a plaquette between horizontal and vertical singlets, and that's actually important in the theory that tells us that we may have continuous transitions, that should be able to happen. If we have these kinds of dimer arrangements, you actually don't have those kinds of fluctuations, because the VBS then also will be a staggered kind of VBS, similar to the staggered state that John mentioned for the quantum dimer model yesterday. So one would definitely expect the transition to be first order in this case, and it is. Okay, so yeah, so now I wanted to, let's see. I have some movies here, but I think there should be one slide before that, so the slides are in the wrong order. Sorry about that. Let me talk about this slide first. So let me talk a little bit about this 1D case where, similar to the J1, J2 chain, we can go between a critical phase and a dimerized phase. So the dimerized phase is of this form. So this was studied in these two papers pretty much at the same time. So Kedar Damle just arrived today, so he was behind this paper here. So we basically did same things here. So to confirm that we had this kind of phase transition and study some aspects of that. So let me just show you a movie that one can generate from this projector QMC, which maybe illustrates really what the VBS is when you add fluctuations. So what is shown here is what happens when you, in the projector simulation, you act with this operator string, which, as I mentioned, reconfigures valence bonds in certain ways. And then you take these transition graphs by overlapping bra and ket states. So here this is done in a sort of floating way in this space of operators, that you move the location where you form the transition graph. And then you will sort of see the dynamics of this process. So this is in a case here where Q over J is very large, so that the system is really quite strongly VBS ordered. So you see that this is, the outer arches here correspond to the valence bonds in let's say, the bra state, and the inner ones in the ket state. And this is then the transition graph loop, transition graph represented in this ring-shaped lattice. So you see that they have mainly short valence bonds, and they line up in the bra and ket state, and you can understand that they want to line up because that's how you maximize the number of loops, and that increases the overlap between the states, and that comes in the projector scheme as well as part of the weight. But then you see that there are some places where you have some defects, and you can actually think of those defects as spin-ons. So you have some longer bond, and inside that longer bond you have places where the bra and ket VBS has a mismatch, right? And then you see, if I run the movie again, you see the dynamics of that those longer bonds appear and go away and so on. Right, and then you can, okay, so now I have this other movie here, I guess. It was in the wrong order. So here is a case where we increase the J coupling a bit, so we have more fluctuations. And then we can see what happens when we go all the way to the critical point. So then you really start to get fluctuations where you get really long bonds. Because now this dimer pattern is breaking down completely. Okay, so this gives you some intuition what the valence bond solid is in the presence of fluctuations. Now let me talk about something more related to spin-on. So I can actually consider an extended valence bond basis for higher spin states. So basically you do a mixed basis of spins, let's say up, if you consider Sz equals S, and the remaining spins are paired by valence bonds. So this was also studied by Keder and collaborators. So basically if you look at just some piece of these transition graph loops in such a mixed basis, if we look at the singlet sector, everything is paired up into bonds and the transition graphs only have loops. But if we look at the case where we have a spin 1/2, that would correspond to having an odd number of states. Then some of these valence bonds don't close. So there's an unpaired spin in the bra state and the ket state, and those form ends of a string. So you can think of this actually as a spin-on. So there's only one spin-on there, but the location of this unpaired spin can be different in the bra and the ket state. So in some sense, the unpaired spin is not the spin-on, but the whole string is a representation of the spin-on. And that also tells you immediately that the spin-on actually has some size. It's not just on a site. Now if you go to spin 1, you have actually 2 spin-ons in the system, as shown here. So this would be one spin-on, and the second one just happens to be the shortest possible one where the unpaired spins are on the same side. So one can actually use this basis to make some statements about spin-ons in the system. So let me just illustrate that by a movie. So this is a case where we actually have an odd number of sites in the system. So one of these unpaired spins is in the bra state and one is in the ket state, which you don't see so clearly here, but they're just colored differently. So when I run this movie, you will see that these blue and red circles, they tend to stick together. And that's because they really constitute one single spin-on, but that spin-on has some size, but it moves about in the system. Okay, what happens if I have 2 spin-ons in the system? So now we're back to a chain with an even number of sites. So we have 2 spin-ons, but there will be 4 circles here. Green and blue corresponds to one spin-on, and blue and red corresponds to another spin-on. And you see that they tend to avoid each other because the spin-ons here are deconfined. And it turns out they even have a very weak repulsive interaction between them in the in this JQ chain. So they spend more time far away than close to each other. Okay, so one can make some quantitative calculations here, regarding, the size of the spin-on, and if you go to 2 dimensions, you can even really look at spin-ons in 2 dimensions and ask if they are confined or deconfined. But let me not do that. So that was the end of what I wanted to finish yesterday, and now I already spent, I guess, 20 minutes on that today. So are there any questions about this part before I move on? Yes? Is there any limit on the distance between those 2 spins which are part of it? You only, define, you mean the 2 spins in the spin-on? Well, no, in principle they can go, as far away from each other as half the system size, but if you make the system very big, then, the probability of going very far would be very low. I mean, they are exponentially, the distribution of distances is exponentially decaying, turns out. Yep. Anything else? Okay, so let me move on to what is lecture number 3. So now I want to talk about how to actually use QMC methods of the kind that we have discussed to study phase transitions. So those could be quantum phase transitions which take place at 0 temperature as a function of some parameter in the Hamiltonian, or we may also be interested in finite temperature transitions in quantum systems. I will show you examples of both. But before I show examples, I want to say a few words about the kind of finite size scaling techniques that we use to analyze data. Right. So, as I mentioned already, we could have transitions driven by thermal fluctuations, even in quantum systems and in classical systems. Of course, thermal fluctuations is always what's driving the transition. And if we are at 0 temperature, we can regulate the amount of quantum fluctuations by some parameter in the Hamiltonian. And if we just look at the order parameter in the two cases, it looks quite similar. We plot as a function of temperature or as a function of that parameter, whatever it is in the Hamiltonian. And in both cases, we can have first order or continuous transitions, right? So in the first order transition, at some point, the order parameter just jumps. And in the continuous case, there's some power law behavior. In the first order case, the correlation length remains finite at the transition. And in the continuous case, we have a correlation length that diverges with this exponent that we call nu, either as a function of the control parameter or as a function of the temperature. So this kind of picture already indicates that maybe there are similarities between the quantum and classical transitions, and there are many similarities, and there are some differences as well. So let's look at a simple case. Let's look at the Ising model. So I think everybody has done mean field theory of the Ising model. So what you can do in mean field theory, for example, you can look at the Ising model as a function of the magnetic field, and you see that if you are below the critical temperature, the magnetization will jump from up to down at some point. And if you are above TC, there's just a smooth variation. And if you are exactly at the critical point, there is some singular dependence. So if you stay at 0 field, you can look at the symmetry broken magnetization as a function of the temperature. So exactly at 0 field, we can, if we go below TC, we can have either up or down. So here I just plot the up, the positive M branch, and it looks like that. Now when we do simulations, we of course don't do mean field theory and we have finite size. But as I mentioned already, normally we compute the squared order parameter because we actually don't break the symmetry. So if we are below TC and we study an Ising model, we would in principle fluctuate between the state with mostly up and mostly down spins. And so if we compute averages, we should get that M is 0, but M squared is not 0. So if we look at M squared for different system sizes, and these are Monte Carlo results obtained with cluster algorithms, so the error bars are very small. You can see for a small size, M squared as a function of t doesn't really show much of a phase transition, although maybe you can start to suspect that there is something. But as you increase the system size, it becomes clear that there's really a non-analytic behavior developing there. So one way to analyze this data is to look at fixed temperatures and look at the results as a function of system size. So that's shown here at 3 different temperatures. So if we are above TC, then M squared should just decay to 0 as a function of size. And that will actually happen with a trivial power. It will always go like 1 over the system size. Okay, and if we are in the ordered phase, of course, we eventually converge to some value. As you see here, if we are far below TC, the convergence is very fast. If we are closer to TC, the convergence may be or will be slower. If we sit exactly at the critical point, that's when we get non-trivial power law scaling. And here the slope would be related to some of the critical exponents of the model. And that's how we can extract the critical exponents from finite size data. So here I would like to emphasize that here finite size is not or should not be seen as a problem. It's actually what allows us to look at critical scaling. Okay, so some people may tell you, oh, we cannot look very close to the critical point because there the correlation length is always bigger than the system size, so this should not work. But that's exactly why finite size scaling works, it turns out, when the infinite size correlation length is larger than the system size. So I want to talk a little bit about that. So let me talk about the finite size scaling hypothesis, which I guess a long time ago was conjecture, based on experiments and simulations. But later, of course, it has been put on a very firm footing by the renormalization group, but I will not discuss that. So if we look at a physical observable as a function of system size and temperature, for example. In general, this will depend on both the temperature and the length in some way. And since the correlation length, if we are close to a critical point, is in a simple way related to the temperature, we could also say that it depends on the correlation length, the infinite size correlation length, and the finite length L. So if we go to some limit where the correlation length is much smaller than the system size, then the system size L should not matter anymore. On the other hand, if we go to the case where the correlation length is much larger than the system size, then that correlation length should not matter anymore. Actually, now I'm wondering if I should actually show another slide with the same material. At some point I decided, okay, I will not show this slide, I will take this slide from a more recent talk which was better, so I forgot to delete the old one. Okay, but this is saying pretty much the same thing. But more clearly, okay, the correlation length is so now I'm just talking about some distance from the critical point, delta, so it's T minus Tc, and that's the correlation length. And if we look at some quantity in the thermodynamic limit, then the system size should fall out, as I already mentioned. So then we expect that there's a power law dependence as a function of the distance from the critical point. And here kappa just depends on what quantity you are looking at. So kappa here is just some generic exponent. Now what you can do is you can write delta as a function of the correlation length and use that here. So then you get that this quantity A goes like the correlation length to minus kappa over nu. Okay. Now if we look at Tc or very close to Tc, then we can say, well, in some sense the correlation length can no longer grow, and then maybe it should be correct to just replace the correlation length by L, and it turns out one can make that argument very, very firm. So what one should do is just to go from thermodynamic limit scaling to finite size scaling. You should just write things as a function of the correlation length, and then you just replace that by L. So then you see that you get this exponent combination governing the L dependence. Okay, if we want to look at a little bit in more detail, then one can use this finite size scaling hypothesis that I started to talk about. So A of L of t, according to the hypothesis, is basically that critical power law times a function which is a function of just the ratio of these two length scales. If you use the form of the correlation length, you can put that in here, and then you can take a power of that and say, okay, that becomes some other function of delta times L to 1 over nu. So this is the finite size scaling form that one expects. And again, I have not told you exactly why, just some hand-waving things, but it can be derived basically from RG. But let me show an example that this really works. So here, again, I have some results for the two-dimensional Ising model. So this happens to be the susceptibility for several system sizes. And in the case of the Ising model, we know all these exponents. So what we can do is to multiply my quantity, which is the susceptibility in this case, with, or I should say divide by this power here. So in the case of the susceptibility, that minus kappa becomes gamma. So this corresponds to dividing out the power. And then on the x-axis, if I want to find out what this scaling function is, then I should plot my results as a function of delta L times L to the 1 over nu. And in this case, I know exactly what TC is because this model has an exact solution. So we can just do it, and this is the result. And we know for the Ising universality class all the exponents as well. So you see here that we get data collapse, at least if the system is big enough. So these small systems, I guess the labels vanished, but these curves that deviate a little bit, those are for the smaller system sizes. So eventually, if we have big enough system size, if we have scaled it this way, the curve collapse should continue forever. But for the finite systems, there will be some peeling off at some point, and there will be deviations. But if the system is big enough, in principle, any value of the scaled x-axis should be fine. Okay, so if we don't know what TC is, or we don't know the exponents, in principle you can make a kind of fitting procedure. You try to find the parameters that best collapse the data. So that's one way to find TC and to find the exponents. But one can do something more sophisticated as well. Let me mention what's called the Binder ratio and the Binder cumulant. That turns out to be something very useful, especially to extract the critical point, the location of the critical point, but also the exponents. So what I show up here is the order parameter distribution. And again, it's for the Ising model for simplicity, but in principle, there are such things for other models as well. So the order parameter, which is just the total magnetization divided by the system size, so it's between plus minus 1. It's just a scalar in this case, so it's a one-dimensional variable. And I can accumulate the histogram of the probability distribution of M in the simulation. And if you do that, what you will find is that if you are above TC, in this case, the temperature is 2.6. TC is around 2.27, by the way. Then you see, just a broad maximum here. If you do a small system size. If you go to a bigger system size, you see that the maximum becomes sharper and it starts to look like a Gaussian, and that's of course because at high temperatures the fluctuations are just Gaussian when the correlation length is much smaller than the system size. Now if you go below TC, you will have order in the system, but if you don't break the symmetry, the order can be either of the up or down kind in the case of the Ising model, so M will have one peak for negative values and one peak for positive values. And again, as you go to a bigger system size, those peaks become sharper and they eventually become Gaussians as well, because the fluctuations, again, are Gaussian. So what one can now do is to form a dimensionless ratio, and you can do many kinds of ratios. The most popular one is to take the fourth power of the magnetization, that's the expectation value of that, and divide it by the second power squared. So that's what we call a Binder ratio. Now if we look at this ratio for t is less than tc, it's very easy to see that it will be 1 because you know, when the system becomes really big, these Gaussians, we can just treat them as delta functions. So if we just compute the expectation value with a delta function, we just get, you know, m4 is the same as m² squared, right? So this ratio goes to 1 below Tc. If you are above Tc, then you have Gaussian fluctuations, and by just evaluating Gaussian integrals, you can see that this ratio goes to 3 in the Ising model. So this value here would depend on what kind of order parameter you have. If it's some higher dimensional order parameter, the value would be different, but again, you can calculate it by Gaussian integrals. And this one would be 1 no matter what kind of order parameter you have. So the Binder cumulant is defined in such a way that it, you know, using this ratio in such a way that it goes to 1 below Tc and it goes to 0 above Tc. So it's just a combination of the ratio and the constant and multiplied by some other constant. And this expression includes the number of components of the order parameter. So it's n1 for the Ising model. Okay, so that's very useful because now we can look at some data, and we know that in the thermodynamic limit we should see a step function. So you see, if we go to increasing system sizes, in fact it becomes more and more like a step function. But if you look closely around Tc, you know, if you zoom in, for finite size it's never really a step function. And an interesting aspect is that these curves cross each other essentially at one point. Sometimes there's some drift, as we will consider later, but eventually, for big enough system sizes, one expects these curves to cross exactly at the critical point, and that's very useful. So it turns out that the drifts in these, that these critical points, crossing points, drift quite fast toward the critical point, much faster than, for example, the peak in the susceptibility that I showed you before. That can also be used, but this is actually better. So the Binder cumulant is very useful for extracting the critical point and some other things as well. So let me discuss what we call crossing point analysis. This is sometimes called phenomenological renormalization. Actually, it was introduced by Michael Fisher originally a long time ago. So what you can do is look at, for example, system sizes that are differ by powers of 2. So, you know, here L, 16, 32, and 64. And here I have really zoomed in very close to where these curves cross each other. So one can basically, from the kind of finite size scaling form you expect from RG, when you also include corrections to scaling, which come from irrelevant scaling fields, you can derive an expression for how those points drift. And I will skip the derivation, but basically the result is that the horizontal crossing point goes to Tc with a correction which is L to minus 1 over nu plus omega. And here omega is the smallest of these irrelevant exponents. So in the case of the Ising model, it turns out that this omega, if you look at the Binder cumulant, is 7/4, if I remember correctly, so it's quite a big exponent. So if you look at the data, you know, Monte Carlo data, you can basically fit some high-order polynomials to these data points and extract the crossing points that way, and you can do error analysis and so on. So these are data points obtained in such a way. And this is a fit to just a constant plus L to some power. I didn't fix what the power is, and then of course one can, in principle, use that power to get these exponents. But you see that this kind of drift analysis works quite well. And since this is the 2D Ising model, we can actually test the scheme. So what you can do if you want to be statistically correct, you can, well, so you see that there's some deviations for the smaller system sizes. So and those come from some higher order corrections that we are not included. Here we only included one correction. So you can throw away the small system sizes until you get a statistically sound fit. And then you can say, okay, this should be okay because the fit doesn't show any statistical problems. So with this data here, you get actually TC of the Ising model to, what is it, almost 7 digits accuracy, which seems insane, right? And it's in complete agreement with the actual result. And here, really, the only thing that was done was to say, okay, we use this form, and then we do the fit with increasing, with more and more sizes thrown away until the fit is okay, and it works. Well, the reason why it works so well for the Ising model, and I think actually, everybody at some point who does these things will look at the Ising model, and it works so well. So then we get spoiled and misled, and we believe, oh, it should always work well like that. But actually, it works so well here because this correction exponent is very large in the Ising model. Depending on what quantity you look at, it can be either 2 or something close to 2. So that's why this convergence works so well. So I will show some examples later today where you will see it doesn't work that well. But even if you go to Heisenberg or ON models, things like that, omega is quite large, close to 1. So it also works quite well in those models. But other more interesting models can have smaller omegas, and maybe there are several omegas that are almost of the same magnitude, and that also causes problems. So it's not always so easy. Okay, so that was about finite size scaling. So if anybody has questions about that part, I can maybe answer those now before moving on to some quantum systems. Okay, so let's move on. So now I want to discuss one relatively simple example of quantum phase transition that we can have. Actually, yeah. Yeah. Yeah, that's right. Yeah, so that, yeah, good point. So that would just converge as L to the 1 over nu without, this omega here. Yeah.
Same question. So it will take, to get those corrections correct, I have to go to bigger system sizes.
Yes, exactly. So yeah, if in general if this omega is small here, it would be better to go to bigger system sizes. But actually, you could in principle also include higher order corrections in the fit, right? So it's not always clear what's better, to go to big enough systems where you don't have corrections to the leading corrections, or to do smaller sizes and do more accurate calculations. It's not clear. Well, sometimes it's clear, sometimes not. I'm not sure if I really answered your question, but we can talk later. Okay, let me look at a class of quantum phase transitions. Actually, John already mentioned yesterday this bilayer Heisenberg model that I show here, where if this J2 interaction is very large, you basically form singlets there, so it's a kind of boring state. It becomes less boring if you go close to the critical point where there are lots of fluctuations. So you can dimerize systems in many different ways. So also if you do it, for example, in this way, if these red couplings here are much stronger than the blue ones, you form singlets, and it's the same kind of physics. So what you expect in general in these kinds of models, if you tune this coupling ratio that I call G, is that you go from some null state, eventually to something that is close to a singlet product state, But in between there's actually a quantum phase transitions where the fluctuations are large and the correlation length diverges and so on. And just by symmetry you would expect that this should belong to the universality class of the 3D classical, Heisenberg finite T transition. And there has actually been quite a lot of work on this, and it turns out that, I will not talk about it, but let me just mention it, that there are some of these dimerized models that have some very anomalous behaviors that were, for a long time confusing people, and there were even suggestions that there are some cases, including this one, for example, where maybe it's actually not the Heisenberg universality class, but now it's known that it is. But depending on how you make this dimerization, you may or may not have one of the corrections that you normally don't have in for example, if you look at the O3 model. But I will not discuss that further. One interesting thing here is that there's actually a three-dimensional realization experimentally of this kind of dimerization transitions. I will talk about that a little bit later. A lot of work has been done on it, thallium copper chloride. I will talk about it later. So let's just look at these 2D dimerized models first. So we can do things similar to when we look at the Ising models to look at the critical point. Some things look a bit different just because we have a continuous symmetry instead of discrete symmetry. So for example, if we look at the staggered magnetization, if you remember in the Ising model, if we went below TC, the curves converge very quickly on top of each other. But here, the convergence is much slower, and that's related to the fact that these models have a continuous symmetry, not discrete symmetry. But in the end, it's quite similar. So I already showed you the 2D Heisenberg model, the data for the 2D Heisenberg model. That's repeated here. So this is zero temperature results as a function of 1 over L. And this is how that scaled. We looked at that already, and I told you the value. Now if we look at other coupling ratios, so we just look at some fixed value of G here as a function of size. You see if we go to G equals 3, it's quite clear that there's no order anymore. And it looks like the critical point should be around 1.9, just if you look at it roughly. So now we can do the Binder cumulant and look at things more carefully. And again, one can analyze the drifts of these crossing points. And one can look at other quantities as well. So you can look at what's called the spin stiffness, which is like an elasticity constant of the Nell state. And you can look at the correlation length. You can look at lots of things, and they all should scale in the same way, and you should get the same critical point. And as you see here, for different quantities, the corrections look different, but they all scale into the same crossing point. So from that we can extract quite an accurate value for the critical point. Now, okay, so one can extract other things from these crossing points as well, but you can look at the data in many different ways. So let me look at one maybe pedagogical way of looking at scaling. So we can look at the Fourier transform of the spin operators, and we can measure what's called the static structure factor. It's just SZ of minus Q times SZ of Q. We could choose any component we like, or even S dot S. It doesn't really matter here because the system is rotationally invariant. So that's the static structure factor. We can also look at a susceptibility. So this is the Kubo formula for the susceptibility. So you put on some magnetic field at wave vector Q, and you measure the response at the same Q, and that's the response. So the order in wave vector is pi pi, so you expect peaks at pi pi if you look at these in momentum space. Now you can also extract the correlation length from these things. So this is referred to often as the second moment definition of the correlation length. So you take this structure factor, which is really just the Fourier transform of the spin-spin correlation function. You look at it at the ordering wave vector and the smallest distance in momentum space away from the ordering vector, which is 2 pi over L. Take that ratio, subtract 1, take the square root, and multiply by this thing here. That gives you a measure of the correlation length, it turns out. So these things one can look at. So if we look at S of pi pi, similar to what I told you about before, there's some power law divergence, and here it's something which has a positive exponent, so it really diverges as a function of size. And then there's some smaller power of L as a correction, and something similar for the susceptibility, although I should rename these constants. It's of course not the same constants. The eta should be the same, but A and B are not the same. So we can just, since we extracted the critical point to some insane precision, we can look at the behavior at that point and maybe at some neighboring points to see how sensitive things are. So here we expect eta to be very small, because in the 3D Heisenberg class, eta is around 0.03 or something like that. So I divided S of pi pi by L, then it should be almost a constant if I have this kind of critical scaling, up to this correction term here. So these are for 3 values of G very close to the critical point. And you can see initially for small sizes, it's nothing like a constant. So you expect this actually to be decaying with a very small power of L, right? Because eta is something like 0.03. So, but for bigger sizes, it starts to look like that is the case. And one can fit the data, including the corrections, and that's actually these curves that are shown here. So doing that, one can extract eta. The values are slightly different from the 2 quantities, but within statistical errors, they are sort of okay, and they are very close to what is the best result from classical simulations for these exponents. So here I just showed what is the role of the correction by, after having done the fit, I just show what you get if you exclude the correction term. So you see that the correction is actually quite important always for these system sizes, even if the system is, well, reasonably large, 128 or something like that, squared. Okay, so that's how we can analyze, critical points which really happen at 0 temperature. But now let's talk a little bit about what happens at finite temperature. And this is one of the things that is special about quantum criticality. So you may know that if you look at classical critical systems or just thermal phase transitions, it may actually not be easy to see the critical scaling. You may have to go really, really close to the critical point to actually see power laws and extract the exponents. So the experiments are not so easy to do, I guess, for that. I mean, of course, people have looked at helium and things like that, and one can do something. But one special thing with quantum criticality is what's called the quantum critical fan. And here I show the situation for a 2D Heisenberg kind of system. So this is based on this famous Chakravarti, Halperin, and Nelson paper in 1988, where they sorted out this kind of thing. So if we look at a sort of phase diagram here, actually this is not really a phase diagram, because in 2 dimensions, by the Mermin-Wagner theorem, you cannot have Néel order at finite temperature. So you only have Néel order or any order at all at 0 temperature if G is less than this critical value. And beyond that, you have a non-magnetic quantum paramagnetic state. But there are some what people call regimes or scaling regimes at finite temperature. And this is some things that one can understand from some field theory treatments and probably other arguments as well. So it turns out that when the temperature is roughly less than the relevant energy scale of the null state, which is the spin stiffness. So the coupling J is the microscopic energy scale, right? But the actual physical macroscopic energy scale is something else, and that vanishes at the critical point, and it's the spin stiffness. It's basically an elasticity constant of the antiferromagnet. So below that temperature, and it's not a sharp temperature, so that's why I just show this wide shaded region here, because it's a crossover. So roughly below that temperature, the system actually, in some scaling sense, behaves as a classical Heisenberg model. So this is called the renormalized classical regime. And renormalized just means that the stiffness has some renormalized value. Okay, on the other side, you have a gap in the spectrum, and that's the energy scale. So below that energy scale, basically, you get rid of thermal effects very fast, and you have a finite correlation length and so on. But what's really interesting here is what's called the quantum critical regime, which falls in what's called the fan between those. And here, the behavior of the system in a very wide regime is actually controlled by the critical point. So this is something that you don't see in classical systems. And the reason why you have this in quantum systems is that if you think about the path integrals that we discussed on Monday, you have mapped the system to a classical system with one more dimension, right? You have the imaginary time dimension. But that's a finite dimension. It has a finite size in the imaginary time direction, which is 1 over the temperature, and we can call that L tau. So now what was done in this paper is to basically do finite size scaling in that size. So you have a two-dimensional system, but you have an additional dimension which is finite. The spatial dimensions are infinite, so now you have just one size, and you can apply finite size scaling arguments. And then this actually is similar to the finite size scaling that we already discussed. So from those arguments, one can derive quite a lot. So for example, this actually applies for a system that has dynamic exponent z equals 1, which is the case for these antiferromagnets. But in principle, one can write down expressions that involve z as well, but this is for z equals 1. So for example, the correlation length should diverge if you sit roughly above this critical point and look at the temperature dependence. The correlation length should diverge as 1 over t. The specific heat should go like t squared, and the susceptibility, the uniform magnetic susceptibility, should go like t. Okay. So these are things one can test with QMC studies. But in this case, we really want to go to the limit where we take the system size to infinity, so that we can really study the temperature dependence of these quantities without size effects. So then what you have to do basically is to do simulations for different system sizes and see where the results converge. And you always expect faster convergence at higher temperatures than lower temperatures, because basically the system size needs to be larger than the correlation length. So the correlation length is small at high temperatures and large at low temperatures. So you see here, if I look at the susceptibility, and here I divide it by t, because as I mentioned, the expected temperature dependence is t linear. So if I divide by t, I expect it to be roughly constant, which you can see it's roughly, the scale here is quite fine. So you see that you have some relatively strange finite size effects, but eventually things fall on top of each other, and you can consider those converged results as thermodynamic limit results. So this plot here is just zooming in on this behavior here. So what you expect basically from those Chakravarti-Halperin-Nelson arguments is that chi over t should go to a constant, and you see that it does, but there are some important corrections as well. So if we just plot the susceptibility as a function of t, you see this linear behavior. Now, as I mentioned, these behaviors here, they should, strictly speaking, apply down to 0 temperature if you are exactly above the critical point. But even if you go a little bit away, they should hold with some relatively small corrections. So for example, in the case of the uniform susceptibility, you see that it's still roughly linear. It's just shifted a little bit. So if you fit a line, it goes to a negative or positive value. If you go much lower, you would see that the behavior changes. It will scale to a finite value, and of course here it will scale to 0. But roughly, you still see these behaviors. So this is one important aspect of quantum criticality, that actually the 0 temperature critical point actually affects the behavior even at quite high temperatures, as you see here. So in that sense, it may be, quantum criticality may be quite important even if you are not at really low temperature. Okay, so one can actually go beyond what I did here and really analyze things carefully and compare more quantitatively with field theory predictions. There are 1 over n predictions. You can generalize the Heisenberg model to n components and do 1 over n calculations. So for example, doing that, you can be more precise here. You can predict what the prefactors actually should be. Okay, you can read about it in one of these. In this paper, Arnab Sen again was involved in this work. And actually, well, I will not say much about it, but the 1 over n expansion may not be as good as people had believed, I would say. Okay, let me talk about this 3-dimensional system that I already announced. So here we finally can see some experimental relevance of these things. So there's this thallium copper chloride system. So it has been studied, a lot using neutron scattering in many papers, especially from the group by Christian Rüegg at PSI in Switzerland. So this is a paper from 2015. This material has quite a complicated structure, but the main point is that it consists of dimers. So there's copper atoms that appear in pairs in some sense. So there's a relatively large coupling between those copper sites. And okay, this graph is a little bit messy, but basically it's a network of these dimers. So the dimers are coupled to each other in several different ways, but this is the strongest coupling here. And what can be done experimentally, and this is maybe, I'm not sure it's the only example, but it's at least the best example where one can really go between the Nell state and the paramagnetic state experimentally, and it's by pressure. So you see in atmospheric pressure, so this is kilobar here, so I believe that 1 here means 1,000 atmospheres. Which is not that high pressure, so they can actually do neutron scattering in those pressures. So in atmospheric pressure, it's in the quantum disordered phase, and then you can bring it into the Nell phase. It's not known exactly how the couplings change as a function of pressure, but apparently, relatively speaking, the intradimer coupling is weakened so that the system has less tendency to form these singlets, so that you actually go into a Nell phase. Now in this case it's 3 dimensions, so we can have Nell order at finite t. So one can look at the Nell order as a function of the pressure, and they have looked at various things, and again one expects this kind of quantum critical scaling regime there. So I'm not going to say much more about the experiment, maybe a little bit, but let me talk quickly about some work that we did, inspired by this material a few years ago with my former student, Sungbo Jin. So we looked at not the full crazy-looking dimer network in that material, but we wanted to see if we find some sort of universality, not just in terms of the universality class of the transition, but beyond that. So we looked at 3 different types of dimerized 3-dimensional lattices. So one is basically a 3-dimensional generalization of the bilayer. It's like a bicube, and these other cases are just simple cubic lattices with some dimerization. And then we, using the kind of scaling techniques I talked about, we determined the Nell temperature, meaning the finite ordering temperature of the antiferromagnet. And we also determined the order parameter at 0 temperature. So again, we can look at drifts of crossing points of various quantities and extract the Nell temperature for a fixed coupling ratio. And then we want to look at the ordered moment at 0 temperature. So we do calculations at very low temperature, basically take the limit t goes to 0 and the size goes to infinity at the same time, and we extrapolate the order parameter. And what we wanted to do was to avoid having to deal with the fact that, in the experiment, they don't really know how the couplings change with pressure. So they can plot things as a function of the pressure, but not as a function of some coupling. So one way to avoid that issue completely is to look at the Nell temperature as a function of the ordered moment at 0 temperature, because that doesn't involve the couplings at all. So that is shown here, but you see I have 3 different graphs here because there's a little bit of a problem, how to normalize the Nell temperature. So we have 3 different models, and they have some similarities, but they are different in some sense too. And of course, the temperature is an energy scale which depends on the microscopic parameters in the model. So you can normalize, for example, the Nell temperature by one of the couplings. That's done here, and then you see we get 3 different curves for the 3 different materials, and that has to do with the fact that, well, there's more than one coupling in the system, so maybe you should not just normalize in that way. So here we have normalized by something which is, it's really the sum of all the couplings connected to a given spin. So it's a sort of mean field coupling strength, if you will. And then you see that these basically collapse on top of each other. So in that sense, the Nell temperature seems to be universal if we normalize it in this way. We can also normalize in a different way, which may be more easy to deal with experimentally. Namely, we can extract some temperature scale from the fact that the susceptibility always has a peak as a function of temperature in an antiferromagnet. So the peak value shifts with the coupling ratio G, but we can take the peak value as an energy scale of the system, and we can normalize it with that. And then it collapses even better, but then there's also some other, so basically in all cases here you get a linear behavior, which you actually expect from some rather simple mean field arguments. Let me not get into that, but one can make some simple ansatz for decoupling of the thermal and quantum fluctuations and write down something that gives you a linear behavior if that decoupling holds, but if it doesn't hold, you get some deviation. So we believe that this signifies something where quantum and thermal fluctuations become mixed because the temperature becomes high, when the ordered moment becomes high, the Nell temperature also becomes higher, so you get more excitations of the system. Anyway, without getting into too much details of that, let me just show you that this was actually tested in this paper that I showed. So our work was stimulated by an earlier paper from the same group, and then they did some more work, and they tried to see if they could reproduce this slope that we had gotten here. So it turns out that this normalization by the peak value of the susceptibility is something that they can sort of do experimentally. I don't think it was they don't really have results of this quality, but at least they had some results that allowed them to claim that they normalize in that way, and then they got these results here. So a little bit similar to what we got. So this line here is something I added myself, so that's sort of roughly a line that roughly goes through those points. It's not exactly the slope we predict, but it's, I think I say it somewhere, something like 25% different. There's some uncertainties, like the G factor and all sorts of things. But still, this shows that you can do something that experimentalists can be happy about here. Okay, so now in the remaining, I guess, 15 minutes, right? Something like that. Now I want to talk about more interesting systems. So John already mentioned yesterday that the really interesting physics in spin systems come when we have an odd number of spins per unit cell. So in the dimerized models, we have 2 spins per unit cell, and that's driven by this singlet physics. And okay, there are actually many interesting questions still to study in terms of the criticality. For example, dynamics, which I will talk about tomorrow. But these models with 1 spin per unit cell, they have some more complex behaviors that I want to talk about. And again, John mentioned some of these things yesterday. So it's again, so here I really want to again start from the Heisenberg model and imagine that I add some other interactions that are also SU2 interactions, so they don't break this spin rotation symmetry. So it's useful to think in terms of valence bonds here when we think about the kinds of ground states we can get, as John also mentioned yesterday. So the RVB would be if we just restrict ourselves to short bonds, which of course by itself is an approximation, but at least it illustrates the concept of resonating valence bonds, that you have a wave function that is a superposition of all the possible bonds. And then we can have, so that's one thing that you could get from the Heisenberg model if you add some other interactions. Another thing that you could get is some state where these valence bonds like to crystallize, so that's what we call a valence bond solid. The French always call it a valence bond crystal for some, which I guess is better, but most people I think call it a valence bond solid. So as I already mentioned, the valence bond basis is overcomplete, so in fact one can describe any kind of singlet state in the singlet sector with valence bonds. But what we are interested in is these types of states, and of course there are many states within in those classes. So normally the non-magnetic states are dominated by short bonds, whereas if you want to describe an L state with valence bonds, if you don't break the symmetry, you just describe the L state of the finite system. That involves a lot of long bonds. Okay, so we would like to study those things. So, one motivation for, what I'm going to talk about a little bit today and mainly in the Friday colloquium is this so-called theory of deconfined criticality, which is about the phase transition between the antiferromagnet and the VBS. So this is something people have been thinking about for many years. Well, it got very dark and silent. Good. But there were some new twists to the story in 2004 when these people here suggested that this is actually should be a continuous quantum phase transition, which had not really been proposed before. People had considered, within field theory approaches, how you should describe the VBS and so on, but there was somehow one piece of the puzzle missing. So, but this is a bit unusual because normally if you have an order-to-order transition and the symmetries are not, the broken symmetries are not related to each other, one is not a subgroup of the other, you would expect that to be a first-order transition, or that there should be some coexistence of the phases. But the claim was that this should be a generic continuous transition. Okay, so they discussed this within a field theory. Let me not actually get into that because it will take too much time, and I'm not even really an expert in these field theories. But the point is that they made a very concrete proposal, and then they did, again, large N generalizations and they, of this field theory, which is called the CP_n-1 theory, and they did large N and 1/n calculations and so on. But the big question, if you go to large N, this is what you get. Actually, the field theory itself, as written, only describes, that doesn't describe the VBS, but it describes the critical point and the null state. But the claim is that, or the conjecture was that this should apply also for n equals 2, so for the normal electronic spins. But other people have claimed that it should actually be first order. It has been quite controversial. So one way that people have been thinking about these VBS states, of course, is with frustrated interactions, and I already talked about this a little bit in the first lecture, so I think I can go very fast here. So we know that it's hard to study frustrated interactions. There may be a valence bond solid state here, so you may be able, in principle, in this kind of model, to go between the null and the VBS. But there may also be a spin liquid somewhere in between, or just a spin liquid. Nobody is really completely sure yet. Numerically it's hard because of sign problems, and other methods are not really, let's say, mature enough to really settle the issues yet. So we can study the JQ models. I already have mentioned a few times that the JQ model has a valence bond solid state, and it has, of course, the null state. So we can look at the null and dimer order parameters and see how they behave in the JQ model. So we have already discussed the null order parameter. Let's discuss the dimer order parameter a little bit. So this is the kind of dimer pattern we have in mind. So these again should be singlets. So the singlet strengths can be measured just by these nearest neighbor correlations. And then we have to put in some phase factor to correspond to the kind of pattern we have, and we can have the dimers, the singlets in the X or Y orientation, so the dimer order parameter is really a two-component order parameter. So then we compute the squares of those, and then I just want to flash some results here. I'm not going to discuss things in too much detail, but we can see something that looks like critical scaling. So J over Q around 0.0447, that's where we believe the critical point is, and you can see that we get some power law behavior for both D squared and M squared here. And it turns out that actually what we get from this finite size scaling approach is these exponents eta for these two order parameters look very similar, and you may ask if they are actually the same. There's a recent work by John Chalker and collaborators who actually propose and show some evidence in a different model, but a model which should also have this deconfined criticality phenomenon. They actually propose that there should actually be a new emergent symmetry, O5 symmetry at the critical point, which would mean that the null and VBS order are different components of the same, actually it should be SO5, I have a typo there, not O5. That's a very interesting proposal, and people are very excited about it and try to confirm it in various ways. Okay, so it turns out that this exponent here, we are not super confident about this value and other exponents that have been extracted. So many groups have worked on this JQ model and tried to get the exponents, and it became clear at some point that there are really big corrections to scaling. So the exponents change a lot as one goes to bigger sizes. So we need to try to do things systematically and go to bigger sizes if needed. So let me just show some of what we did in a recent paper here, looking at the Binder cumulant. So this is a slightly different Binder cumulant from the one I showed you before. Before I showed the fourth power and the second power. This is the second power and the absolute value squared, but that's also a fine one to look at. We have looked at both, but this one seems to behave a little bit nicer. So again, we can do a crossing point analysis, but now you can see an example where this looks not as nice as it did in the Ising model. So you remember in the Ising model, the horizontal crossing point, which goes to the critical coupling, it had a really nice monotonic and fast convergent behavior. Now in the JQ model, you see that this is completely non-monotonic, and you know, probably at this point, once you get past this minimum here, around system size of 30 or so, it is monotonic. So you know, that's what we have to assume here if we are going to do anything at all, and it's probably true. So then we can again try to extract the critical point, and we can analyze exponents. So it turns out that, okay, I already mentioned how we expect those to asymptotically go with size. What I didn't mention is that you can extract 1 over nu from the slope of those Binder curves. So if you look at two system sizes, the Binder cumulant will, or you don't need to go to the cumulant, you can just look at the ratio as well. The curves will cross each other, they have different slopes. The bigger system has the bigger slope. So if you take the ratio of two slopes, you get actually something that should be related to 1 over nu in a simple way again with a correction. So this is what's shown here. 1 over nu star is you know, the finite size crossing value from the finite size crossing point, and it's plotted as a function of 1 over L. And we expect this kind of correction, so we fit it to a power law correction with a power that we determine. And you see that it works quite nicely. But the correction exponent is quite small. It's around 0.4 or something like that. Well, 0.4, 0.5, whatever, something like that. So it's not so easy to actually, the uncertainty is pretty big in the extrapolated value. But we get something which is around 0.45. And that, interestingly, turns out to be very close to the value that John and his collaborators got for this other model that I mentioned, where they actually looked at even much bigger system sizes. And we don't see any first order transition. By the way, if we have a first order transition, then the exponent nu should always be 1 over d, 1 over the dimensionality if we do finite size scaling. So one can still see scaling at the first order transition, but the exponents have trivial values. So, you know, if you want to be the devil's advocate here, you know, you could say, oh, well, maybe this goes to 3. It looks like it's going up. Well, it is going up, but on the other hand, it fits quite well with this power here. So I don't personally believe it goes to 3, but I wouldn't bet my head on it. Maybe I would bet my arm on it, but not my head. At least I would bet $10, okay? Oops, sorry. Okay, so let's see, I'm almost out of time. So let me just flash some things quickly. Maybe I should continue something next time again. I have a few more slides. But one thing in the remaining few minutes, we have also looked at the finite temperature phase diagram of the JQ model. So in this case, since the VBS breaks continuous symmetry, it will actually have a finite temperature phase here. So it's also interesting to look at the finite temperature phase transition and ask what kind of universality you have. So this is a case where actually you don't expect a fixed value of the critical exponent. So we have an order parameter which has a 4-fold symmetry. It's a Z4 symmetric. You can translate and rotate this pattern by 90 degrees, so you have 4 different patterns. So then if you look in, okay, this is a finite temperature transition, and we are in 2 dimensions. So if you look at conformal field theory, we can actually have cases with varying critical exponents. So in this kind of symmetry, what you expect basically is a C equals 1 conformal field theory, and those have varying exponents. And there are actually two different, let's say, branches of criticality you can have there. So as a function of some model parameter, which in this case is Q over J, you can have a case which is realized in, for example, the Ashkin-Teller model and some other models as well, where at one end you go to basically two coupled Ising models, so nu is 1, and in the other end you go to a four-state Potts universality class where nu is 2/3, and in between it's varying. But eta is always 1/4. So this is what's referred to sometimes as weak universality, because eta is fixed, but nu is not fixed. But there's actually another possibility. Again, at one end you can have an Ising transition, and then in the other end it actually goes to the Kosterlitz-Thouless transition where nu diverges. So this happens, for example, if you put a cosine for theta term in the 2D xy model. When that term becomes very weak, it becomes an xy model and you go to KT transition. And when the term becomes very strong, it becomes two coupled Ising models. So it's interesting now to ask, okay, is one of these scenarios realized on this curve in the JQ model? So I will go a bit faster. So we have calculated again some quantities and look at the scaling. So in this case, we look at correlation lengths. So these we are looking at the dimer order parameters. So if we look at the correlation length, it can be different if we go on the horizontal or vertical axis here. So if we look at momentum space and you use this second moment definition that I talked about before, we can go in momentum space like that or like that, and we can get two different correlation lengths. And it corresponds to going horizontally or vertically when the dimers are oriented like that. So we can do finite size scaling with that and extract the critical point. So we can look at crossings of psi over L and look at the drifts, and again we can look at the two different correlation lengths, and they give us the same critical point. We can also look at the data in other ways, and we can confirm that eta is very close to 1/4 as is expected. Then we can do data collapse, or we can analyze nu in the way I just told you about, but we can do data collapse and get nu from that. And this is the last slide I want to show. So quite interestingly, what we do see is that we get the ordering temperature as a function of Q over J. So here we used actually the Q3 model because it has a stronger VBS ordering. As TC goes down, the nu exponent actually becomes very large. You see it becomes almost 3 here, which is consistent with this Kosterlitz-Thouless scenario when TC goes to 0, which is also consistent with this deconfined criticality scenario that I will discuss more on Friday, where we have emergent U1 symmetry. So one aspect of emergent U1 symmetry, if I go back to the phase diagram, oops, sorry, where is that? Here. Is that we have emergent U1 symmetry at this point. So normally you think about that happening at 0. So happen when we approach it seam to sea. It would be nice to go to even lower temperatures and make sure that that really continues, but at that point this was the best we could do. Okay, so I actually did finish. Sorry I took a few more minutes, but thank you a lot for your attention.
So you showed your phase diagrams as a function of some quantum G, critical parameter and temperature. And in both cases, for large values of Q or G, it was a gap phase.
This phase is not, this is a gapless phase. The null phase is gapless.
Right, that's right, but the disordered or the VBS is gapped.
Right. Oh, yeah, right. In that
Right.
sense, yeah.
You may also have a gapped, like, I mean, this quantum spin liquid gapped. What do you expect in that case?
Right. You mean in terms of the criticality, or? Yeah. So people have worked out, or at least proposed field theories for the nail going to spin liquid phase transition. So that should also be a kind of deconfined quantum criticality, but with different exponents. But I'm afraid I cannot say more than that. There's a field theory proposal, but I don't remember any details of it. It would be, of course, very nice to study, and that actually may happen. I guess you were not here on Monday, where I discussed a little bit some recent DMRG results for the J1, J2 Heisenberg model, where we may have actually, we don't know for sure yet, but it has been proposed that there could be a gapless spin liquid, not a gapped spin. Well, okay, other people have proposed a gapped spin liquid, but it's completely unclear. But that's another scenario, right, that you have a gapless spin liquid. But there are not many models where we can really study those in any unbiased ways on large lattices. So this is a case where at least we can do QMC on large lattices, and we can really provide some, well, at least eventually, hopefully, some really definite results.
Anything else? If not, then let's thank Anders again.
Thank you.